All right, in this video, what I want to do is I want to start the material for linear algebra. And what we're going to do is we're going to start by thinking about an object or a problem that you've undoubtedly seen in high school algebra class. So what I want to do is I want to think about how would we solve something like the following system of equations. Let's say we have 2x plus 3y equals 8, and 4x plus y equals 6. And so what I want to do is I want to think about what's the solution of this system going to be. And one thing that's going to be very helpful for us as we go along and think about these systems of equations is to think about this problem geometrically. And so what I mean by that is that we have, if you think about these as lines, these are going to be my axes here. So we have our xy axis. We have the line 2x plus 3y equals 8. That's going to look something like, I'm not being very careful here, but that's going to look something like that. And then we have 4x plus y equals 6. So let's think about what that's going to look like. Here, for the first line, 2x plus 3y equals 8. When y is 0, x is 4. So that's the point 4, 0. And when when x is 0, y is 8/3. So something like 2 and 2/3, 2.67. For the other line, we have 4x plus y equals 6. So when x is 0, y is going to be 6. So that's way up here. Okay, so this is the point 0, 6. And when y is 0, x is going to be 6/4 or 3/2. So this is going to be 3/2, 0. And so what this is going to look like is we're going to have two lines. There's a terrible line. That also was a terrible line, but I'll live with it. So we have two lines. And what we want to do is we want to figure out what's the solution going to be. In other words, what's the point here? What's this green point that's on both lines at the same time? So we want to solve the system, figure out all the values of x and y that solve both equations at the same time. And there's a few different ways that we can go about this. One way that we can go about this is just by substitution. So you can take this bottom equation and solve for y, and then plug that into the top equation and go from there, and that's totally fine. One thing that's going to turn out to be very useful for us as we go along through the semester is to solve these not by substitution necessarily, but by what's called Gaussian elimination. Gauss was perhaps the best mathematician to have ever lived. And he did a whole bunch of stuff. His name is everywhere, from probability to number theory, combinatorics, geometry, everywhere. His name is just everywhere. So, and linear algebra, of course. Gaussian elimination is where you take a multiple of one row and add it to the other. So there's a few different ways that we can do this, but I think the easiest way to do this is to take our top equation, and what I'm going to do is I'm going to multiply our top equation by -2. And the reason we choose -2 is that if I take -2 times 2x, that gives me -4x. And then if I add that to the second equation, that'll cancel out the x terms. So what I want to do is I want to actually just get in the habit of rewriting this entire system of equations. And so this system is going to become, we're going to have -4x, -6y equals -16. And the bottom equation we haven't done anything to, that's going to stay the same. So we have 4x plus y equals 6. And so now what we can do is we can add the two equations together, cancel out the x's. You've probably already done this. You're probably working ahead here a little bit. -6y plus y is -5y. -16 plus 6 is -10. This tells us that y is 2. Okay. That seems to somewhat agree with the value that we have, by the way. That seems a little reasonable given what we have. So y is 2. And then once we know that y is 2, we can take that value for y, plug it back into either equation, and figure out x. So if we know that 4x plus y is 6, and we know that y is 2, that means that 4x plus 2 has to be 6. So 4x is 4, and therefore x is 1. So that means that our solution is going to be 1, 2. Okay, so our solution is 1, 2. And I want to think about just solving these systems of equations. Being able to actually solve this 2 by 2 isn't, doesn't take a lot of work to do that. But I want to think about what are the different options. So we have 2 equations and 2 unknowns. And I want to think about what are the different options that we're going to have when we solve these systems. And if we think about just 2 equations in 2-dimensional space, or 2 lines, I should say, in 2-dimensional space, we have 3 options, basically. Either the 2 lines are going to intersect at a common point, like they did here. Okay, so they had 1 point of intersection. The other 2 options are the 2 lines don't intersect at all, they're parallel. And then the third option is that the 2 lines intersect at every point on the line, meaning it's the same line. So if I had the same line sitting on top of itself, those 2 lines would intersect at every single point, and there would be infinitely many solutions. And so it turns out there's only 3 possibilities. Okay, so there's only 3 possible solution sets. I should say 3 possible types of solution sets. And that's where we have a single point, like we had in our example. We have the empty set. There's no points of intersection. So this is what happens when the lines do not intersect. And then there's also the occasion where the 2 lines overlap completely and there's infinitely many solutions. Okay, so infinitely many solutions. And that fact is going to be actually more important than we may realize right now. And we'll revisit this and things like this as we go along. Okay, so that's all I want to say about that one. Let's do one more like this, or at least one more. So the next one that we're going to do is going to be 3 variables and 3 equations. So I want to look at the system. I want to solve 4x plus y minus z equals 10, x plus y plus z equals 6, and 2x minus y minus 3z equals -2. And what I want to do is I want to start to kind of formally think about what are the operations that we're allowed to perform here. And it turns out that there's 3 elementary operations. So there's 3 elementary operations. The first is, and this is not something that we think about necessarily when we do these by hand, but we're allowed to switch any 2 rows. We're allowed to switch any 2 equations. Okay, so if I want to write these 3 equations in a different order, it's going to be the same system. Hopefully that makes sense. I'm allowed to multiply any row. So multiply any row by a non-zero number. Okay, like we did before. So in the first example, we multiplied by -2, but we can really do it with any non-zero number. You can actually do it with any, you can do it with a 0 as well, and your result will be true. It's just not useful, right? So that falls into the unfortunate mathematical category of true but not useful. So we insist that we multiply by a non-zero number. And then again, like we saw before, we can add any two equations. Okay. I said row before, so just to be 100% clear, when I said row, I meant equation. What we're going to do is we're going to start talking about we're going to kind of stop talking about thinking of these as equations and start thinking of these as matrices. So that's kind of where we're headed. But for now, let's just stick to talking about equations. And let's think about how can we do this as easily as possible. And so what we're going to do is I want to use the fact that the top equation, or I'm sorry, the middle equation, x plus y plus z equals 6, already has a 1x in it. And that's going to tell us essentially how do we use that to our advantage, right? So what I want to do is I want to take, and there's two ways to do this, but what I want to do is I want to take multiples of that middle row and add them to the top and bottom so that the other x's cancel. And the way that we're going to do this is let's actually first switch the rows so that that one's on top. X plus y plus z equals 6, and then we'll copy the others. 4x plus y minus z equals 10. 2x minus y minus 3z equals -2. And so what I want to do is I want to multiply the top row by -4 and add it to the second row. I keep saying row. Take the top equation, multiply by -4, add it to the second equation. Take the top equation, multiply by -2, add it to the bottom equation. And we could do that, but in order to minimize the number of steps, what I'm going to do is I'm going to think about these two operations over here is basically the same thing. So instead of thinking about the 3 elementary row operations, I can really think of items 2 and 3 as a single operation. If I multiply any row or any equation by a non-zero number, and then I can also add it to the second equation. So really what I'm saying is that another way to think about add any two equations is I can actually add any multiple of any equation to any other equation. That's another way to say basically the same thing. So that's what we're going to do. And I want to keep track of how we're going to go about this and how this is going to work. So I want to carefully keep track. So I'm going to call these row 1. So row 1, row 2, and row 3. And what I'm going to do is I'm going to start by adding row 1 times -4 to row 2. And so the way that I'm going to write this is that our row 2 is going to become row 2 minus 4 row 1. So we're going to take -4 times row 1, add it to row 2. That'll be our new row 2. And so what's going to happen then is our system is going to become, so the only thing that's going to change is row 2. So the top and bottom equations are going to stay the same. So x plus y plus z equals 6. 2x minus y minus 3z equals -2. And then the middle equation, what we're going to do is I'm going to take -4 times the first equation, add it to the second. So we're going to get -4 times x plus 4x. So it's going to be 0. And that's by design. That's why we pick the -4, remember? And then -4 times y plus y. So that'll be -3y. And -4 times z plus -z. So that's -5z. And we have to do it with a constant too. So -4 times 6 will be -24. Plus 10 will be -14. Okay. And that's our first step. And then the next step is we're going to do it with the bottom equation too. Okay, so we're going to replace the third equation by itself minus twice the first equation. And now the only thing that's going to change is the third equation. It's the only thing that we're changing. And so I'll copy the other two, x plus y plus z equals 6. -3y minus 5z equals -14. And then the bottom equation, we're going to take -2 row 1, add it to row 3. So we're going to get 0x. And then -2y minus y is -3y. -2z minus 3z is -5z. And then 2 times 6 is negative 12, minus negative 2 is negative 14. And so what happened here is that the bottom two equations are actually the same, and they don't give us any extra information. So it turns out that even though we started with 3 equations and 3 unknowns, this is really something that can be reduced to two equations with 3 unknowns. And so this bottom equation is not going to be very useful. We can ignore that equation that we just highlighted in blue. So our goal now is to solve the rest of it. So we're going to try and figure out what are the solutions going to look like. So now what we really have is we've reduced this to a problem of having 2 equations with 3 unknowns. So negative 3y minus 5z equals negative 14. And again, there's lots of ways to go about this. All I'm going to do for now is I'm going to take row 2 and replace it by negative 1/3 of itself, so that the constant in front is going to be a 1. That'll just help us with our algebra. So this means that our system is going to be x plus y plus z equals 6. So that part we haven't messed with. And then negative 1/3 of the second equation is going to give us still 0. Y plus 5/3 z equals 14/3. Okay, so that's a 5/3 there. All right. So far, so good, I hope. And then we have just one more step. I'm going to take minus row 2, add it to row 1, and that'll be our new row 1. So row 1, we can simplify a little bit. We can get rid of this y term. So if we take row 1 and replace it with row 1 minus row 2, what's going to happen is we're going to get, now row 2 is going to stay the same. Y plus 5/3 z equals 14/3. And let's see, that means that the top equation is going to be x, because here I have a 0x. So any multiple of that is still 0. And then we add that to row 1. So we get just row 1. So we get the x term there. Here, the y's are going to go away by design. And then if we take minus 5/3 z plus z, that'll be minus 2/3 z. And then 6 is 18/3. So if we take 18/3 minus 14/3 will be 4/3. Okay, so there we go. And then this is our system. So it turns out that all solutions to the system, so all solutions look like this, look like x minus 2/3 z equals 4/3, and y plus 5/3 z equals 14/3. And we'll talk about geometrically what that's going to look like, but the way that we can actually figure out geometrically what it's going to look like a little easier is that we're going to what's called parameterize our solution. So any any point x, y, z that satisfies those equations will be a solution for us. And notice that there's a z in both equations. So what I'm going to do is I'm going to let z be our parameter t, and then we can solve for the other variables in terms of t. So our top equation is going to be x minus 2/3 t equals 4/3, and that becomes x is 4/3 plus 2/3 t. In the bottom equation, if we plug in z equals t, is going to be y plus 5/3 t equals 14/3, and that's going to translate to y equals 14/3 minus 5/3 t. And so our solution set we can write as a few different ways. The way that we wrote it up here is good enough for now. I mean, it's not the best way, but it's good enough for now. A better way, though, is to write it in parameterized form. So this is the same kind of parameterization that you did in Calc 2, how you parameterize different solutions. And so what we're going to do is we're going to talk about our solution set being all the points x, y, and z, where x has to be of this form 4/3 plus 2/3 t. Y has to be of the form 14/3 minus 5/3 t, and z is t. And now it's clear what all the solutions are going to look like, and any value of t you can plug in to get a solution. And so this is called a parameterization of the solution set. Okay, because we've written everything in terms of this common parameter t. Now, the reason why that's useful is that this helps us picture geometrically what's going on. It turns out that our solution set is going to be, so we have three equations and three unknowns. So the fact that we have three unknowns means that we're working in three-dimensional space. And these are x plus y plus z equals 6. These are planes. And so if we think about how we could intersect planes, there's a few different options that we have. If all three planes are the same, then your solution set's going to be any point on that plane, and you're going to have kind of a two-dimensional solution set. Dimension is something that we'll talk about rigorously later. If I have two planes that intersect, so you have to think of if I have two sheets of paper and they pass right through each other like this, that place where they pass through is going to be a line. And then that line is also going to have infinitely many solutions, but it's going to be a one-dimensional solution set. And if I have three planes and none of them do anything funny, they're all kind of just generic planes, then there's two things that can happen. One is that any two planes will intersect along a line. If that third plane intersects that same line, you got a single point. Okay, so if you have three planes that intersect, they can intersect at a single point, or it's possible that you have three planes and they don't intersect at all. So it's kind of like if you were to have three lines, I can really only draw in 2 dimensions, and even that's a stretch. But if I were to have three lines, right, if I were to have any two lines that are not parallel, they would intersect at the same, at some point. And then some third line may go through that same intersection point, or it may not. Okay, and so there's, in this last case, that's what I'm talking about when I have the third plane doesn't go through that line of intersection. There's no solutions. In our case, what happened was we have infinitely many solutions because there's infinitely many values of t that'll work for us, and it's a one-dimensional, it's a line. So our solution set is going to be a line. I know it's one-dimensional because the dimension is the number of parameters that we have, and we have just one parameter t. Okay, so that's how we know it's going to be a line. All right.